Welcome back, everybody. Hope you enjoyed the long break. So it gives me great pleasure to welcome back Isha Powers from IBM, and she's going to be talking to us, giving us a crypto update around the Z16. So Isha was going to come and talk to us at the conference in November, but unfortunately she wasn't able to join us due to some travel issues. So we have her now, which is really lovely to see you again. And I was just saying that it's an incredibly early start for you. It's like 4 a.m. now, isn't it? And
yes, exactly.
yeah, so thank you so much. And just as an FYI, Isha has got 2 sessions today. So we've got this session, and then at 2 o'clock UK time, Isha will be back with us to give us more crypto updates. So without further ado, welcome back, Isha, and the stage is yours.
Thank you so much, Jamie and Sisu and the whole team that's helping in putting all of this together. I'm sure it's been a lot of work this week. And I just want to say welcome to everyone who is joining. Again, my name is Isha Shireen Powers. I'm based here in the US, specifically in Los Angeles. So as they said, it is very early here, but that's okay. We're gonna have some fun this morning. I am trying to follow the chat as well. So feel free if you have questions, if you have thoughts or any comments, feel free to use the chat. I love the interaction and communication. The goal for this session is by the end of the session, you guys will be quantum experts, compliance experts, all these cool features of Z16. You guys will be experts and SMEs for these features. At least that's my goal. So if you don't know me before, my background is in crypto and security for mainframe. I've been in this area for about, it'll be next year, it'll be officially 20 years. So I'm happy to answer any questions that you have. I find crypto and security to be fascinating, fun, interesting. So yeah, so let's go and let's have some fun for the next hour about Z16 and what we can do today with crypto. So Z16 is built to build, and that's a story that's centered not just on security and crypto, but also around AI, modernization, automation, and those things as well. Now, of course, from our perspective for this session, we're going to focus specifically on security capabilities. But it's just important to think that IBM Z, of course, is a huge platform, many different operating systems, many different features and capabilities, just to help you and your business to operate as best as it can. So let's go ahead and let's dig into like the fun security stuff. So when we think about Z16, we think about being secure and having a cyber resilient system. So let's kind of dig a little deeper. How many of you guys have heard about quantum safe cryptography? I'm looking in the chat to see if any response. Has anybody heard of quantum? And I think there was a session earlier this week, so there should be, yeah, I see a thumbs up. I see a few thumbs there. Great. Awesome. So we're going to take you through first some of the quantum features. For those, some of you may know this already. So for those experts, they can just kind of sit back and go, And then for those who are new, feel free to ask questions. We're going to talk about quantum safe cryptography and really get a feel for like what it really means to you. Because sometimes you hear about the cool phrase and you hear about superposition and qubits, and you're trying to say, well, how does this make sense? How does this fit in with what I already know about crypto and security? It just seems kind of high and lofty. But the goal in this session is to kind of bring it down so that you really understand what quantum is, what it means to you, and what is supported on Z16. And then we'll get into compliance. And in the backup, I don't know if I'll get there, but I also have some material on ZS 2.5 and some of those security updates. So let's start with quantum. So quantum safe crypto refers to efforts to identify algorithms that are resistant to attacks by both classical and quantum computers to keep information assets secure even after a large-scale quantum computer has been built. Very, very interesting. So specifically, it talks about classical, and then it talks about quantum computers. So let's kind of dig into that. Let's start at classical, right? That's what we know. That's what we have today. So that's where we're going to start our journey. So when you think about classical cryptography, you might think of pervasive encryption, right? The idea with pervasive encryption, and I know all of you have been hearing about pervasive encryption probably for the last 4 or 5 years now. And with pervasive encryption, we're talking about making sure your data is protected, whether it's in transit or whether the data is at rest. And even when you think about data being at rest, there's many different places where that data could live, right? So here, let's see, you have your data, some flowing over the network, going into z16. It can go to many different LPARs. Let's say that it goes into this particular z16 LPAR. And for that particular LPAR, maybe you decide to do data set encryption or application level encryption. If you decided to do any of those, then your data is going to be encrypted, as you save it to disk. So as it flows over the storage area network, it's protected, and then it gets encrypted again if you have disk encryption. And although that's more of a z16 story, the same thing for Linux. You can use cryptographic technology to protect your data, and it protects your data there at rest, and you can protect your data as it goes in flight or in transit to other systems. And then even in the middle here with a coupling facility where you have shared memory and you're trying to communicate across different LPARs, that data there can also be protected and encrypted as well. So the idea with pervasive encryption is that your data is being protected wherever it lives, resides persistently, or also wherever it flows within the environment over the network. Now this chart should look kind of familiar as well. It's the famous encryption pyramid. And the idea is that when you think about data at rest, you can think about the data in terms of which cryptographic technology you're going to use, and there are trade-offs between the different technologies. So for example, the bottom of the pyramid here, you see full disk and tape. That is the widest part of the pyramid. And it being the widest part represents the fact that when you use full disk and tape encryption, 100% of the data is protected, which is great. Very easy to turn on. However, when you think about, oh yeah, I have disk and tape encryption, that's all I need. And you start to say, okay, well, what kind of attacks does it protect you against? What kind of risks do you have if you only have that one technology? And then you start digging a little deeper and you realize, yeah, it protects everything, but it only really protects from like physical removal of the disk or tape. So anyone who has access through like a login or anything like that, they still have access to that data in the clear. And your goal as a security administrator is to make sure that only the people that need to have access to the data should have access. And so you're trying to narrow the scope of access and authorization to just those parties who need it. And maybe full disk and tape, though it's great, covers everything, maybe it is a little too wide in terms of allowing multiple people to access sensitive data that they shouldn't. And so you may want to layer on other technologies to kind of further narrow that scope to just the people that need access to the data. So then you say, well, let me do data set encryption, right? Because that's pretty wide. It's not everything, but it's wide. And it's easy to turn on. It's, you can enable a policy. It's great. And then you say, well, what about database level encryption? You can do that for DB2 and IMS. And then at the very top of the pyramid, there's application level encryption. And with that, you have so much control. If you want to encrypt 4 bytes or 4 terabytes, you have that ability by calling different APIs and libraries. As you go up that pyramid, not only do you get kind of like that ability to kind of like scope like what you're actually encrypting and protecting, but you also get a lot of control. So the further up the pyramid you go, that means that you have more control over who can or cannot see that data. So you might say, okay, I'm encrypting everything at the application level because that is the most security control. But there's a trade-off there too. Now you have applications that have to change. You have workloads that may have to change. You're going to need resources and people and skills, and they need to understand those different cryptographic libraries. And so there are trade-offs for these different technologies. And these are some of the things that you guys are thinking about as you're deploying cryptography in your environment. Okay, so let's keep going. Again, we're still in that classical crypto space, and then we're going to kind of go into quantum. So now we're going to look at crypto infrastructure. So we saw pervasive encryption, it's everywhere. There's all of these different technologies that you can use, but underneath those technologies is infrastructure. And core to that, you'll see here, is ICSF. So ICSF provides a couple of different architectures on the ZOS side to allow you to do cryptographic operations. There are CCA services, so that's the Common Cryptographic Architecture. And then there's PKCS11 services, and this is the PKCS11 architecture that used to be RSA, now it's governed by OASIS. And you can see for ICSF has the ability to use different device drivers and make use of different crypto engines. For example, if it wants to use a CCA adapter, it can go through a CCA device driver. Or on the CCA architecture side, it could just call CPACF instructions, right, built into the ZBox. On the PKCS11 side here, you see it has a PKCS11 driver, allowing you to access the Crypto Express adapter, which is configured for EP11. But it also does software crypto, can use CPACF, and funny enough, it could also use CCA. So there's these two different architectures which are underlying many different components. You may be explicitly calling these in your applications, or you may just be using dataset encryption, for example, which calls CCA under the covers. Or maybe you're using communication server, and maybe that's using PKCS11. Or maybe you're using DB2 and that's using CCA services. So there are several components within the operating system itself, which may be using ICSF, and you may not even be aware that those components are using ICSF under the covers. So it's really cool, the breadth and what's covered in ICSF. One thing to note here is that for the different architectures, like I said, there's two architectures. They each have their own key stores, and key stores are where you persistently store your keys, right? So if you are using CCA, your key stores are the CKDS. These are for your symmetric keys, and PKDS for asymmetric. If you're using PKCS11 architecture, there's one key store, TKDS, and it stores all the keys. So just kind of make sure you guys have that understanding that there's two different architectures. They have different persistent key stores, and they can access different crypto engines. Awesome. Okay, now let's go a little deeper, right? So we started high level at pervasive encryption. We looked at data at rest and the encryption pyramid, and then we looked at the crypto infrastructure, and let's go even deeper. So it's like we're just going like here, and zooming in. So cryptographic fundamentals. So we know we want to do encryption and decryption. Well, what does that really involve? That involves taking some data and a cryptographic key. You're going to apply an algorithm that does encryption, and that produces your ciphertext, right? Very easy. And go the opposite direction. You have your ciphertext here, same key, decrypt, same algorithm, and you get back to your original data. So it's this process that kind of goes back and forth. But notice here that the keys are the same. So for symmetric cryptography, the operations use the same key for both encrypt and decrypt. And you can kind of see the formula here. Data, algorithm, and key get you to the ciphertext. If you have a ciphertext, the algorithm, and the key gets you right back to the original data. And what's special about cryptography, as you guys know, is that the idea is that your data is protected even in the presence of third parties. So you're making sure even if you have something super secret, put it in a room of experts, and you give them the specification for it, just like we do today with DES and AES and all of those algorithms. And even given all that information, they still cannot break this crypto, at least on a classical computer. So what are the applications of this, right? So you're thinking application level encryption and database level encryption, data set level, disk and tape, just to encrypted RACF database, which is new. And network encryption, coupling facility encryption. Most encryption is using symmetric operations, and that's because you can take large amounts of data, chunk it into small pieces, chain them together, and you can encrypt a lot of data with even what would be considered a very small key. So that's one of the benefits of symmetric encryption. Let's look at asymmetric encryption now. What's different between asymmetric and symmetric? Well, you might notice that those keys have changed, right? Before it was the same key, that was being used for both the encrypt and the decrypt. That is not the case when you're doing asymmetric encryption. You have two different keys. So what happens is you're trying to send data to your partner. Typically, you're trying to send a symmetric key to your partner. And what you do is you ask your partner for their public key. And you say, hey, I'm Alice and the other person is Bob. And I say, Bob, can you give me your public key so that I can send you some encrypted data? And so Bob sends me his public key. I take his public key. I encrypt the data that I want to send to him with his public key, and I send that over to Bob. And Bob is the only person that has the private key, right? So Bob has the private key, so he can decrypt that data. And now Bob has the data, I have the data. So I've been able to share it to him and only him. And because I use his public key, he's the only person that has the matching private key. So he's the only person that can actually decrypt the data. And that's what's unique about the asymmetric keys. Now, asymmetric keys are used for many different operations, typically key exchange, right? Problem with asymmetric keys is they don't allow you to encrypt a whole lot of data with them, right? They don't do the chaining operations that you can do with symmetric keys, but they're really great for sending across a symmetric key. So you typically see it for key distribution. You want to use symmetric keys to encrypt a lot of data and asymmetric keys to send the symmetric key to your partner. So you see network security, ATTLS, system SSL, any of those operations where you're trying to share with a partner, you're going to be using asymmetric keys. Okay, last one here is looking at integrity. So this is another fundamental of crypto, and that's signatures. So you have signature generation and signature verification, and this uses those asymmetric keys again, right? The two different keys. So first thing you have to do, as I told you before, asymmetric keys, they can't encrypt a lot of data. They can't operate on lots of data. So first you have to take your data, scrunch it into something small. And you can do that by hashing your data. So you see here, you have some data. You apply a hash, which goes one way. It takes that big piece of data and it scrunches it down into a small hash. Now that you have that small hash, you can go and you can apply your private key to produce a signature. Now, what's interesting with this hash is this is one way. So if you have a hash, you're not going to get back to the original data. But what's nice about the hash is if even one bit changes in the original data, the hash is going to change very significantly. So it's a very good way of telling if somebody changed the data from what you thought it should be. Very good for integrity. Now, when it comes to verification, what you need is you need the data. You need that signature that was generated by the person who created the data. And then you just need the public key, right? The public key is available to everybody. And you can verify and ensure that it's integrity, nobody has changed it, nobody has tampered with it. And you can also ensure that it came from the right person, right? Because it will not verify if you don't have the matching public key to the private key that was signed. And you think about this when you're like downloading software and you're installing it on your machine, and they may have a maybe a SHA hash that you have to compare, that you can use to verify that, you know, the data hasn't changed. Nobody is going to put any malware or any kind of other software or embedded anything in that code. And this is important because in having integrity of the software ensures that your stack is safe and secure. Now, here are the cases where you're going to use signatures. So you have secure boot, I'm sure you guys have heard of for Z15. You have signed SMF records, right? Making sure that they're integrity, making sure you can show to your auditor that nobody has tampered with them, signed emails, signed documents, and signed transactions. This is all about integrity, ensuring that nobody has tampered with the data and you know who it has come from. Okay, one more fundamental, and then we can kind of get into, okay, well, how does this actually relate to crypto? We spent the first 15 minutes talking about classical, and you're like, well, I know all of this already. So I'm going to start blending in so you can start to see where quantum fits in. So let's look at one last concept, and that's cryptographic keys. So cryptographic keys, as we said, you have your symmetric keys and you have your asymmetric keys. Your symmetric keys, these are just random numbers. Like imagine like you say, hey, I want 256 bits of random numbers. That's your symmetric keys. They're just random numbers. So there's random number generation that's built into, into the Crypto Express. There's random number generation that's built right into Z. There's software, different libraries that have random number generation. That's all symmetric key is a random number. And so when you think about it, it's like, if it's only a random number and I wanted to break into somebody's crypto, all you would have to do is guess every combination, right? And so the reason we have these long keys like 256-bit AES is because it takes much longer to be able to find or figure out what a key is. Now, when you have DES, which is only 56 bits, it is very easy to brute force attack a DES key because it's so small. Imagine that, a bit is 2 values, right? 0 or 1, and you have 56 of them. So you think 2 raised to the 56th. That's the number of combinations you would have to try to break a DES key. And it's very easy to do, even with today's classical computers. So don't use DES, don't use DES at all. AES, now think 2 raised to the 256th. And now you're like, okay, now that's difficult, even for today's computers. Your kids, grandkids, today's computers, no, they're not breaking that. Now, asymmetric key pairs, these are the ones that are like the public and private key, and these use complex math operations to create essentially these trapdoor functions where you can easily go one way, but not the other. Meaning if you have a private key, you can get to the public key, but if you have the public key, you can't get back to the private key. And we use this, of course, as we showed before with asymmetric crypto for signatures and for key exchange and key distribution. And these are your RSA keys, your elliptic curve keys. Okay, so I think we have a good fundamental understanding of the basics and all the underlying crypto behind all the cool pervasive encryption capabilities. So envision a skyline. So you're in a city, whether you're in London or maybe you're in Los Angeles or New York, or maybe you're in Nairobi, you're in a different country. So either way, imagine you have a set of buildings there. And in this case, our buildings are different capabilities that you may be using for pervasive encryption, like application level or DB2 or data set encryption and signatures and network security and secure boot. And underneath these buildings, keeping them up nice and strong is a foundation. So this is your foundation. It is these cryptographic algorithms that we just talked about. We talked about symmetric. We talked about asymmetric. The symmetric algorithms like DES and AES, and the asymmetric like RSA and elliptic curve. These are your foundational blocks underneath these buildings. So all of these cool technologies that you are using are all sitting on top of these really, really, really strong, hopefully, foundation. And that's what's holding them up and providing the security you need. However, I did say one thing, right? I said that using DES isn't necessarily a good idea. So why don't we go ahead and we're just going to drop DES, right? So now we have our buildings, we still have our skyline, but we're going to drop DES. So now instead of you saying DES and AES here, we know DES is old, you shouldn't be using DES. So we're just going to remove that one. So now if you really want to have a better, more solid foundation, you're going to make sure that all of your symmetric operations are using AES keys, and they can go up to 256, right? Okay, that's reasonable. But now let's look over here on this asymmetric side. I'm sure many of you have heard of the last 3 or 4 years that a lot of the standards bodies have been looking at eliminating RSA because the keys are so big. And so the idea is that instead of using RSA keys, they recommend using elliptic curve keys instead. So let's go ahead and let's do that. So our crypto skyline, solid skyline today, should be more like this, right? Where you have AES on your symmetric key side or symmetric cryptography, and you're using elliptic curve on the asymmetric side. So this is today, classical computers, the ideal scenario is that these are your strongest algorithms. These are what's recommended today. Now, I would like to ask, how many of you have only AES and elliptic curve in your environment? I've asked this before at a few conferences. I get different answers, but from what I've seen, everybody wants to move to this direction with AES and elliptic curve, but there are some challenges in trying to get there as well. But ideally, this is where you want to get to, where you have these two strong foundations underneath your cryptographic technology.
No one's confessing, Isha. I think there's a mixture. Shame on you.
I noticed that. I was like, the chat's not going. There's no. I completely understand that nobody wants to it. Awesome. Okay. So quantum computers. We're going to enter this quantum world, right? So we talked AES and elliptic curve. That's our ideal. Oh, I see an answer there. Awesome. Oh yeah, in a bank it is. Yeah, there are challenges moving between algorithms because you have to make sure that your partners, whoever you're sharing data with, has to be able to support the same algorithm. So yeah, in many cases that there's a transition period, and it can be a bit of a challenge. So thank you, dear. So let's kind of like start shifting our brains now. We know about classical, let's start looking at quantum. So quantum computers can in principle perform certain mathematical algorithms exponentially faster than a classical computer. Now that's interesting. I'm curious how this would apply to any of the technologies that we just mentioned. Interesting. We talked about symmetric keys, right? Symmetric keys are random numbers. And we talked about how you could, if you really wanted to try to break a symmetric key, you would just try all the different combinations. You would brute force attack. But when you look at like something like look at a DES key, 56 bits versus a 256-bit AES, one is super easy to break and one is pretty much impossible in a classic computer. But when you look at here at Grover's algorithm could be used to speed up a search for symmetric keys or reverse a cryptographic hash. That could be a little scary in our world. We'll have to see what that means for us and our algorithms that we're using. Additionally, Shor's algorithm. Factoring and discrete logarithms can be used. And those are pretty much the underlying math behind RSA and elliptic curve. And they can be broken with a quantum computer. That's also interesting things to be just a little concerned about. Let's dig into Grover's just a little bit more about that random number, because you may have heard this before, where someone say, hey, well, you understand that DES, the smallest DES key is 56 bits, and you understand the largest AES is 256 bits. And sometimes you hear people say, oh, well, with a quantum computer, it chops that in half. And you're like, okay, it chops it in half. Like what part? So here, you're looking at the math. Let's say, like I said before, you have a classical computer. You have two, right? There's 2 bits, 0 and a 1, and there's 256 of those. So if this is for your largest AES key, is 256. So the classical computer, the number of combinations you would try would be 2 raised to the 256. Now, looking here at Grover's algorithm, what it does is now it's half. So it's, in this case here, square root of n raised to the 1/2. Now we take that, our n is 2 to the 256, putting those together, now 2 to the 1/28 combinations. So essentially you went from having 2 to the 256 combinations, 2 to the 128. And this happens to be the same as if you had a 128-bit AES key. So when we talk about quantum and the half, what you're saying is that in the quantum world, a 256-bit key essentially behaves as a 128-bit key. Now imagine if you had a 128-bit key and you started there. Well, that behaves like a 64-bit key. And that gets us in this trouble spot, right? That's not good. So let's look at our skyline now. We got this new information about quantum and these algorithms and what they can do in terms of the math. And our skyline had started here, right? We had DES and we had AES, RSA, and elliptic curve. But now we're going into this quantum era. And with that, before we had DES at risk and we had RSA at risk. But now we also have elliptic curve at risk. And that gets a little bit problematic because when you think about, well, where do you need to be? Yeah, you can go ahead on the symmetric side. You can say, hey, well, you have to use 256-bit AES keys, right? You have to use those large keys because 128-bit is still strong. That's a strong key. But if you had started with a 128-bit key, now you're going down to 64. That would be bad. So you have to make sure that you're using AES 256 if you want to be quantum safe. However, looking on the right side here, what happened to RSA and elliptic curve? Both gone, right? RSA broken, elliptic curve broken, both broken with quantum safe computers. And so now that foundation that you had for secure boot, network security, signatures, audit records, all of that falling off essentially. Like they always tell me in LA, they're like, oh, LA is gonna fall off into the ocean. So essentially here, you have these capabilities that you're probably using today, and the underlying foundation for them is crumbling right now. So you have to start looking at deploying and implementing new technologies and new cryptographic capabilities that will use stronger algorithms. So you can't just continue using RSA and elliptic curve. And you might say, okay, well, I think she's just scaring me. Like, when is this going to happen? Do you need to care about it? Well, you should probably care about it from a few different perspectives, right? If you're a security administrator, you care about this because these are your systems and you're charged with protecting the data. But you should also think about it as a consumer. How many of you use the internet? I mean, we're using it right now. Or how many of you use oil, electricity? How many of you have Bitcoin and cryptocurrency? Anybody use email or payment systems, credit cards? Yeah, all of these different things, from a consumer perspective, they all use cryptography. Specifically, they use asymmetric cryptography. And even for those that are using symmetric cryptography as well, are they all using AES 256-bit keys? If they're not, then those can be broken as well. So where we're trying to get to, our goals, is that we need to kind of get on solid ground again. And so on the symmetric side, you really want to get to AES 256-bit keys, right? That'll keep you on solid ground. Don't use the smaller AES keys, not using DES. And I know I'm making it sound easier than it really is. It does take a transition. It does take some work to get there, but it's important to think about that the technology that you're using underneath those cool capabilities, that technology is weakened in the quantum era. So you have to start looking at how you can move to the stronger protection. And on the right-hand side, so that we don't have these buildings falling off into the ocean, now we have these quantum safe algorithms that you can use basically to replace the RSA and the elliptic curve algorithms that we could use back with classical computers. So you'll hear about crystals dilithium and crystals Kyber. And the reason we're moving to those is because these are quantum safe. Now, the journey to quantum is not necessarily an easy or simple one. As I'm sure you guys know, if you've ever had to move from DES to AES or from RSA to elliptic curve, it's not necessarily simple, but still something that you should look at and still something that you should start working on. First thing that you want to do is you start looking at how do you move to quantum is you need a crypto inventory. You need to know what you have today. Are you all DES? Do you have some AES? But is the AES 256 or is it 128? Do you have RSA? Do you have elliptic curve? You need to understand what crypto is being used. And then if you go to my session, which is, let's see, I know it's 6 a.m. my time. I think your time it's 2 p.m. For those of you who are in Europe, go to that session and we're going to talk about crypto usage information. And this will help you with your crypto inventory. So definitely join that session. The next thing you need to do is you need to start looking at using those quantum safe algorithms, right? There are APIs, there's Crypto Express, you have the z16, which has the quantum safe secure boot. So you have these features and these capabilities that are available now. You just have to start using them. And then you have to do this with crypto agility, keeping in mind that although we're going now, right, from classical to quantum, the idea that you have to kind of move between algorithms isn't new. You guys have been doing that for years now. So you have to think about processes and procedures, that things that are repeatable, that you can do again if you want to move in the future to whatever the next new crypto algorithm may be. Now, if you're trying to get started, there is a really nice red book, Transitioning to Quantum Safe Cryptography. There are code samples. There are all kinds of like helpful information about building that crypto inventory and understanding what you have in your environment so you can move over to quantum. So there's details here. There's a link there as well. You'll have all of these slides. Definitely look and understand more details about quantum and how you can start thinking about positioning yourself for the future. Okay, so I think we're good for quantum. Are there any questions before I kind of take you guys through compliance? Checking the chat to see if there's anything. Okay, hopefully I didn't scare everybody, but yeah, because it's very quiet up there.
One question I've actually got, Isha, is how long do you think it will be before a quantum computer can crack to 56-bit encryption?
Oh, that I don't know, because right now, even at the current quantum, it hasn't cracked even the smaller ones yet. They have to have enough qubits to get to the point where they can crack the different algorithms. I think like I know right now, like NIST has standardized, well, they haven't standardized, they had a competition around standardization for the quantum safe algorithm, specifically like the asymmetric side. But I have gotten the question before about the symmetric side, and the answer is, I guess, probably I don't know. We don't know.
Sometime in the future, maybe. Yeah.
Yes, we don't know when that will be. We don't know if there will be a 512-bit AES in the future, or if it will be like a completely new algorithm for the symmetric side. That's I guess we're all kind of like watching this space, and I'm definitely don't consider myself like on the IBM research side. We have some really super like, mathematicians that are trying to figure out what's going to be next. But right now, we don't know. We're going to stay tuned.
Yeah. I think there was a question came in from Philip, Richard.
Let's see. How does quantum safe algorithms compare to elliptic curve on ZOS when it comes to generating the same key throughput, handshake, forever? I'll have to get you. We normally put out a performance white paper, and I have to see what that is. So we have a performance white paper for the different Z systems, which kind of shows you the operations, how many can be performed per second, whether it's CPACF or Crypto Express. So I don't know off the top of my head, but I'll have to find that white paper and we can check that to do a comparison of what it used to be or what it is for ECC versus what it would be for the quantum safe algorithms. But yeah, great question. Okay, so with that, we'll go ahead and let's kind of dig into compliance. So this is another huge theme for z16. So we're trying to address some of the challenges that you guys may be having and trying to meet various regulatory standards. Okay, so what was driving us looking at compliance? Well, we've heard from you that it is challenging. It's complex. There's many different regulations. They change. There are some regulations that may be there in the UK. There's those in the US. There may be some, whether it's in China or France, there could be many different regulations. There are the ISO standards, things that go across many different areas in payment card industry. But the idea is, how do you keep up with them? How do you ensure your environment can meet those various standards? And how do you do that in a simple way? So we've heard from a couple of clients. Compliance is probably one of the largest business drivers for their policy around security. A second piece is around reputational risk. In order to grow their mainframe business, they need to provide and demonstrate adequate compliance for the departments being brought to Z. And this includes many, many, many different standards. And we're hearing this from many clients. So the journey to compliance looks a little like this and maybe a little different for your organization, but in our work and engaging with clients, what we found is these are the 5 steps that they tend to go through. First, they have to read and understand the various regulatory controls. Then they have to try to translate that to Z capabilities. It's like, okay, the regulation says this, and this is what technology Z has. And so they're trying to reconcile the two. So once they've kind of done that mapping, then they can start to say, okay, well, now I know what these mean. Do I actually have that feature enabled? Like, can they do a comparison and say, are they meeting these requirements? If they are not, then they have to plan and strategize how they are going to meet their requirements. And then they have to implement and demonstrate to an auditor that they are in fact meeting the requirements. Now, there's a couple of huge pain points in this process. One is that translation, because each person has their own interpretation of what a particular control means and which technology it relates to, especially for Z, because many of the different standards were written not necessarily for Z systems, they were written for distributed systems or x86 or cloud. Here, the other challenge is around actually going and proving that you have implemented the actual controls. So to keep up with compliance, there's kind of 3 kind of pillars that we have that we've been looking at and how to ensure that you guys are able to keep up with compliance. The first thing that you guys will have to do is you have to interpret those regulations. So this is the first thing that happens. It's how do you show that with Z that you can meet or exceed industry standards? The next thing that we or you have to do is discover what capabilities are there to meet compliance. There's all kinds of cool features and we're always putting new things out there, but you have to be aware of what's out there and start to enable it and deploy it so that you can meet compliance requirements. And then after you've deployed out, so you've gone through, you know its regulations are relevant, you've mapped them out, then you have to go, you implemented them, and now you have to go and prove it and go through and collect and validate the evidence. These are kind of like the processes that you guys go through and the process that we go through as well as we're looking at compliance. Now, when you go through this, it's not necessarily simple, right? There are so many different regulations, PCI, NIST, GDPR, SOX, you have ISO, I talked about a few others, and then there are region-specific ones as well. And so it gets a bit complicated. But the first one we're going to look at in our example here is we're going to look at PCI, right? We're going to look at the payment card industry. And I'm basing this on PCI DSS 3.2.1 because that's the one that most people are familiar with. But I'll update this also for PCI DSS 4.0. So that way we make sure that we're on the current one as well. But let's look at this. So for PCI DSS requirement 3, you need to protect your stored cardholder data. Great, we know that. Well, there are 7 different sub-requirements under PCI DSS 3. Let's look at 3.4, making sure that you render that account number unreadable anywhere it's stored. This chart looks familiar, right? This is your pervasive encryption, like, looking at making sure that your data is protected, encrypted, whether it's in flight or at rest in different areas in your environment. Question to you is, do you actually know where your PAN is stored? So if someone were to say, hey, you're a bank and you have these credit card numbers, they must be secure. Where is that credit card at any point in time? Is it the database? Is it a data set in a file? Could it be in memory in an application? Could it be flowing over the network? It can be in many different places. And then even if you're in like one environment and you're looking at data at rest, Did you use disk and tape? Did you use data set encryption? Is it encrypted at the application level? Is it at the database level? Maybe. What about other technologies? So besides just the data at rest, what about other components that you might be using? Are you using COM server? Are you using Java? How about that RACF encrypted database, DB2? So there's many different things to consider as you're trying to figure out, okay, what is the control that I have to meet? And then what capabilities do I have in Z to help me meet that control? Because there's many. And then how do I like map all of this out and prove it to the auditor that I'm actually in fact meeting compliance? So one of the challenges you do is you have to map out the capabilities and the regulations. So for PCI DSS 3.4, for example, your first question is, okay, well, where is the PAN stored? Well, maybe you say the PAN is stored in the application. So you say, well, maybe you use application level encryption. And we talked about the trade-offs between these different capabilities, right? But maybe you decided to use application level. And then you're like, okay, well, my PAN data is also in a database. So then you say, okay, well, I'm going to use database level encryption. Yeah, you can definitely do that. But maybe you also say, well, I could also use application level encryption, and that would also protect my database data, right? Because it's kind of like a downstream process. You encrypt it at the application level, then it remains encrypted when it's in the database. Pretty cool. Or you might say, well, I heard about data set encryption and it's pretty easy to do. It has less, the trade-offs are a little bit more tolerable there. So instead, maybe you decide to do data set encryption. So we've already pointed to 3 different possible capabilities that you can do to protect data in a database. Oh, here's another one, disk and tape encryption, right? You can also use disk and tape encryption to protect the data. So this process is not straightforward. Coupling facility encryption, is that data going to be shared across different LPARs? Yeah, you could use that one too. Yes, yeah, you can use full encryption as well for the data. And then you kind of keep going down to all the different places where the data, the PAN, can be stored, and all the different capabilities which are possible. And it just kind of gets more and more and more and more complicated. Because there's many different capabilities that you can use to protect data in different ways. And so let's say you figured all this out and you've mapped this all out and you know which capabilities you're using. You're like, I understand and I've got this figured out, right? As Mark Nelson would say, but wait, there's more. There's different sub-requirements, right? We only looked at one of 7 sub-requirements for PCI DSS. But we only looked at which one? PCI DSS 3. So there's more. There's 12. There's actually 12 PCI DSS requirements, at least for PCI DSS version 3.2.1. So it's like you kind of look at this and it's like you have this one control, you go out to the requirement and then you go out to all of the set of requirements and then right, you're not going to stop there. There's more. There's a new version. So you had just figured it out for 3.2.1. And now there's this new version 4.0. And now you have to go through that same process again. And there are more regulations. So it's not just PCI. Now you have to do the same process for NIST and GDPR and SOX. And if there's a new regulation, you go through the same process again and again and again and again. And it is not an easy process. So what I want to introduce you to is some new capabilities that are in ZOS, and also the z16. We'll talk about that a little bit as well. But there's new features to help you with compliance, and just want to make sure you're aware of those features. Okay, so there's a new ZOS compliance data collection infrastructure, and this was made available. This was made available as part of the ZOS, I think it was ZOS 2.5 continuous delivery in May-June of last year. And I think it rolled back also to 2.4. So with this, there's a new ZOSMF compliance REST API that basically will trigger data collection. And You can kind of see in the dark blue boxes at the bottom, you can kind of see like what's required in order to exploit and make use of this function. But the idea is that you're going to kick off a REST request, which is going to send an ENF signal to a bunch of different components in the operating system. And what those components are going to do is they are going to get that signal, and based on that signal, they're going to say, oh, I just got the compliance signal. Let me dump all of my compliance relevant data into these new SMF 1154 records. So there's new records, SMF 1154, which contains compliance data. And what you can do if you have the Z-Security and Compliance Center that runs, that's a container-based solution. If you have that solution, you can use the CDP, the Common Data Provider, to stream the data over to that solution, and you can see like the visualization, and it will do like checking and things like that. But the idea is that whether you have the z16, which hopefully you'll have, you still are going to have the SMF 1154s, which are in the base as well. So you can use those SMF 1154 records to help you with understanding what features, need to be enabled or should be enabled or may not be enabled in your environment for compliance. And just to give you an idea. So here are a few different components. So for example, let's say you're looking at communication server and you're looking at TCP/IP. Well, previously, if you had, so you're looking at TCP/IP, you'd have to go and try to figure out how do you map these things out? How do you map out the different features that we have and compare them to regulations? So here for PCI DSS, the organization has to use strong cryptography, has to safeguard sensitive cardholder data over the network. Well, what does that mean for TCP/IP? What controls are relevant? If you were had to talk to an auditor, would they understand when you're talking about comm server? There could be some challenges there. And even in demonstrating compliance, there are challenges as well, right? Where do you go to look for evidence that you have enabled this? How much time will it take to find the evidence? Who do you need to pull in? And is the evidence sufficient? Like you might go issue commands, this could be commands TSO and VS, it could be, I guess in this case, it could be USS, could be ISPF panels, SMF records, and who knows which ones those are. But the idea is that now you have these SMF 1154 records. This is part of the base of ZOS, and it has information, is ATTLS enabled? Is packet forwarding, is it disabled? Things like that. There's more than you see here on the list, but this is in ZOS 2.4 and later, and it's available to you. Now, IBM, the Z-Security and Compliance Center is a separate price solution, but what it does is it takes the records here, the SMF 1154s, and creates these really nice dashboards and pulls the information together for you. So in the base, you'll have the 1154s. For the ZSCC part of it, that part is a priced offering. If you have questions, we can get that to you. I don't want this to be a marketing marketing session, but I want to at least make sure that you're aware that that's kind of how these two pieces fit in. But in the base of ZOS, you're going to have the 1154s. And you're going to get this across several different components. So here for ICSF, checking whether or not you're using weak algorithms, that's going to be in the 1154 subtype 49 records. And then here for RACF, you have the subtype 83. You have information there. CPACF, which is new. We're going to talk about that at my next session at 2:00 for UK time, I'll say. And those are the subtype 128s. And again, these are all 1154 records. These are all part of ZOS base, and they're in. You can use this for ZOS 2.4 and later. So overall, compliance data collection, you're going to have like your ZOS side. So this, you're going to have some of this, which it requires the ZSCC. Anything pretty much on this chart that's purple is ZSCC. The other colors are things that are based and are available to you either with the Z16 or available in ZOS. So I tried to kind of show both views. So if you have the ZSCC, you can kick off the process. If you don't, you can still kick off the process, just calling that REST API. And pretty much anything in blue is out of the box. So you can kick off this process to say, hey, collect this data for me. These components here, anything, whether it's in light blue or the dark blue, it will produce these SMF 1154 records. If you have the z16, if you have the purple, then you're going to get additional components that are supported. And you're going to have CDP to stream the data back over there. So you have all the visualization around the data. But the main core is that now you have these SMF records, which contain compliance information to help you with being able to produce the evidence you need to show the auditors for compliance. There is more information, ZOS compliance. You can see more details, and there's a document here. And the other thing I will mention that we do have now is we have CIS benchmarks for ZOS. So CIS benchmarks, these are Center for Internet Security benchmarks, best practices. They exist for cloud and for different on-prem offerings as well. And previously there were benchmarks for those different areas, but we had not had one for ZOS until last year. So huge thank you to my team, the development team, for working on those benchmarks, and now those are available. So you can go out to CI Security, and you can see the benchmark for IBMC. And just because I know we're about 4 minutes left, I'll go ahead and just kind of tie in compliance and quantum. Z16 provides really great capability for both quantum and for compliance as well. It's been one of the focuses for, or at least the themes for Z16. So make sure you use them. And this is a great lead into the session that I'm going to have later on today, where we're going to talk a little bit about crypto counters, crypto usage, and crypto inventory, which are useful on both sides. So go ahead, submit your session feedback, and I'll leave the last, 4 minutes or so for any questions you might have.
Thank you, Isha, for taking us through that. It was beautifully explained. As you well know, crypto is not my strongest area. So I was following and got plenty of that. Thank you very much. So yeah, folks, any questions, you can unmute your line if you like and ask your question to Isha live, or you can post them in the chat. There you go. Look, Kev says super clear explanation of complex stuff. It is complex, isn't it? It's there's so many things we have to think about now with encryption. One of the points that I wanted to pick up with you actually is around PAN data, and you raised a really good point about, well, where is this data? Yeah, and I think hand on people's heart, a lot of people can say, we just don't know really. We know it's here, and here, but where else could it be? I think that's a big problem, isn't it, for organizations?
Yep, absolutely.
Yeah, I have a question. You were showing your the slide with your layers of security, where you can do it at the disk layer and moving your way up. Do people ever use multiple layers for the same data?
Absolutely. In fact, I think most actually do use multiple layers. Like what we'll typically see is most clients have disk and tape. So they'll have that one off the bat. That's usually the easiest one to implement and turn on, right? Because it's built into like most of the storage devices. It's something super easy. But because it doesn't offer protection other than the physical removal, then you'll see, okay, well, data set encryption, that gives at least a little bit more narrow scope. So you'll see that. But then if you're thinking about like banking and finance, they're already coding at like the application level too, right? Because even in some of those cases, they have to create these packets, and the packets have to be signed. Certain parts have to be encrypted. Certain parts have to be in a certain format. And so they may already have APIs or the code applications that are actually invoking the APIs to do crypto at more of like a macro level. So yeah, we often see using multiple. So it's one of the nice things with Z and Z14 and later is that you can layer on these different technologies, and you can do it where the cost isn't so high. So if you were on like Z13 and before, Those were back when the instructions, at least some of this instructions for the data set encryption, specifically on data set encryption, those were optimized in Z14 or later, so you can do more at a lower MIPS cost. So
Okay.
that's one of the things we always look at.
Okay, thank you.
Aisha, just because I did say about using DES, we actually use pervasive encryption to protect our acquirer PAN data, all from the other banks.
Mhm.
So, that's quite good, I think. But, for ATMs and point of sale and stuff, and even the ZMKs to protect those keys, we have to use DES at the moment because it's industry wide.
Yeah.
And then we protect them a little bit by using TR31 and TR34 to try at the moment. But obviously, we'll move on to AES when we can, when all the other banks do, which we'll have to do. So one question, we use RSA a lot, and I've not pushed elliptical curve because of quantum computers and stuff. But do you think we should start using elliptical curve at the moment, or is there any point really?
No, I would say just move right from RSA.
Yeah.
And it's mainly because, so what was interesting is before quantum was, let's imagine there's no quantum. We're not thinking about that. In that world, we were moving from RSA to elliptic curve because the elliptic curve offered the same cryptographic strength for a smaller key. Well, technically, because the key is smaller in a quantum world, the elliptic curve key can get broken faster than RSA in a quantum world. So now it's like, oh no, we have to like switch. It can't be, oh, just go to RSA to elliptic curve to quantum. It needs to be just go to RSA to quantum safe, because elliptic curve, the benefits that we had of moving to elliptic curve are weakened in the quantum safe era. Or in the quantum era. Yeah.
Well, I noticed that, because at the moment we're using, say, TLS 1.2, but in TLS 1.3, that's really elliptical curve heavy. But you've got no choice. So I presume that when we get to say TLS 1.4, hopefully it might have some quantum stuff in it. Yeah.
Yeah, we're going to see a lot of changes in the strategy. Like TLS 1.3, like a lot of it's based on elliptic curve. And it was based on that whole mindset of, like I said, RSA key is too big, move to elliptic curve. So I think from a TLS perspective, yeah, you're going to have to go to 1.3, and then you're going to have to jump after, because I don't think there's standardization yet for quantum safe. And because there's no standardization, that means that you're trying to communicating with, like, if you're communicating internally, it's fine. You're all using the same thing. But if you're trying to communicate with another party, they have to have the same algorithms that you are running, and it's not standardized. So yeah, I think in terms of like network security and those protocols, yeah, you're going to have to use the elliptic curve. But if you have internal applications that are just explicitly using RSA or elliptic curve, and or whether it's for signing or whatnot, I would say to start looking at the quantum safe, like unless you just want to practice transitioning between algorithms again and again, I would say just jump to the one that is going to be stronger in 5-10 years.
Yeah, brilliant. Thanks very much.
So we have another question from Philip. He says, do you know if the new IBM SMF Explorer Python framework supports the new 1154 records in addition to CDP?
Not yet, but I have actually been reaching out to that team to ask them what they were going to support in the future. What they do support is do they support the SMF 30s? They might support the SMF 30s, which does have some of the CPACF data in it. I need to confirm that. If it supports the 30s. But yeah, put in a request for that, because I am also I found out about the SMF Explorer Python framework maybe a month or two ago, and I was like, oh, this is awesome. So yeah, put in an RFE if that isn't there, and I need to check to see if the SMF 30s are there too.
Great stuff. Thank you, Isha. Right, so we're at after 1 o'clock now, and Isha needs some breakfast because it's like 5 a.m. there. So Isha's back with us at 2 o'clock UK time. So I really hope you can join us for more great crypto stuff. And also, Isha made reference to the encrypted RACF database. So there is a session by Mark Nelson at 3:30 UK time to talk about the path to an encrypted RACF data set. So lots of encryption goodies coming up. So enjoy your lunch, everybody. And Isha, enjoy breakfast. And
yes.
Thank you very much. And don't forget your feedback, folks. And we'll see you real soon. Thank you.
Thank you.